Hey everyone, and welcome. Have you ever played a game against a computer, maybe chess, or even just tic-tac-toe, and wondered, how is it so good? Well, it's not just about raw computing power. There's this really elegant, super powerful piece of logic behind it all. And today, we're going to pull back the curtain on the Minimax algorithm. It's kind of the secret sauce for teaching a machine how to play a game perfectly. So yeah, that really is the big question, isn't it? How can a computer play a game perfectly? I mean, making the absolute best, most optimal move every single time. It sounds crazy complicated, right? But the secret isn't about being smarter in the traditional sense. It's about learning to think about the game in a really unique way. Okay, so where do we even begin with this? Well, the core problem, the real challenge, isn't just about figuring out your own best move. No, that's only half the battle. The tricky part is finding your best move when you have to assume that your opponent is also a perfect player. You know, a total pro who's never going to make a mistake and will jump on any chance you give them. You literally have to plan for their perfection. And that right there, that's the heart of the problem. In any turn-based game, you control your move, but you have absolutely no control over what your opponent does next. And remember, they're actively trying to crush you. So your perfect move isn't just a good move. It's a move that stands up to their perfect countermove. So how on earth do you do that? Well, you kind of have to see the future. This is where the Minimax algorithm comes in, and it solves this with a super clever strategy called backtracking. Now get this, and this is the part that might bend your brain a little. It works backwards. To figure out the very best first move, it starts by jumping all the way to every possible end of the game. It scores every single outcome, win, lose, draw, and only then does it start working its way back to the beginning. At every single step on the way back, it asks itself, okay, knowing how all of this could end, what's the absolute best choice I can make right now? It's almost like having a crystal ball that shows you the final score of every possible game before you even made your first move. Okay, so to really get how this all works, we need to introduce the two key players in this whole drama. They're not real players, but they're the concepts that give the algorithm its name. Let's meet Max and Min. Think of them as the two sides of the strategic coin. So Max, that's us, or, the AI we're trying to build. Max has one goal and one goal only: to maximize the score. He's always going to pick the move that leads to the biggest, best possible outcome for him. And then you've got Min. Min is our opponent. And Min's goal is, you guessed it, the exact opposite. Min wants to minimize Max's score. So Min will always choose the path that leads to the absolute worst outcome for Max. It's this constant push and pull, a real tug of war. So what are they actually fighting for? Well, it's a value called utility. And honestly, you can just think of it as points or the final score. A high utility, say +10, that's a big win for Max. A low utility, like -10, that's a win for Min. And 0? That could just be a draw. It's simple. Max is chasing the highest number he can get, and Min is trying to drag him down to the lowest. All right, theory time is over. Let's actually put this into practice and see how it works. And remember, we're going to start at the finish line and work our way back to the start. I know it feels totally backwards, but trust me, you're about to see why this is the only way to lock in that perfect move. So the whole thing really boils down to 3 main steps. Step 1, the computer maps out every single possible move in the game, from start to finish. This map is called a game tree. Step 2, it gets to the very end of every branch on that tree and slaps a utility score on it. Win, lose, draw. And finally, step 3, it starts climbing back up the tree. And at each level, Max and Min take turns picking the move that helps their own cause. Okay, let's look at a really simple game tree here. See those numbers at the very bottom? Those are our utility scores. That's the end of the line, the final outcomes of the game. So we've already done step 1 and jumped to the end. Now, let's start climbing back up and see if we can figure out the best opening move. So we're starting at the lowest level, and here it's Max's turn to pick. Let's look at that first group on the left, node D. The choices are -1 and 8. Since Max is Team Maximize, which one is he going to pick? The 8, of course. So the value of that choice becomes 8. Now moving over to node E, he's got -3 and -1. The higher value there is -1, so that's his pick. Over at F, between 2 and 1, he'll take the 2. And finally at G, between -3 and 4, he's obviously going for the 4. See? At this level, Max just picks the biggest number available to him. Okay, now we climb up 1 level. And whose turn is it now? It's Min's.
Now, Min is smart. Min knows exactly what Max is going to do in the next step. So Min's whole job is to look at the great options Max just picked for himself and choose the path that totally ruins Max's day, the one that leads to the worst possible outcome for him.
So check out node B. From here, Min can see two paths. One leads to an 8 for Max, and the other leads to a -1. What's Min going to do? He's going to be ruthless and choose the path that sticks Max with the -1. He's minimizing. Now let's look at node C. The choices below lead to a 2 or 4 for Max, so Min steps in and picks the path that only gives Max a 2. That's Min's whole strategy. Always limit Max's score as much as possible.
And just like that, we've climbed all the way back to the top. We're at the very start of the game, node A. It's Max's turn to make the very first move. He can go left, towards B, or he can go right, towards C. So now that we know everything that will happen, what's the right call? What's the perfect move? Well, let's think it through. If Max goes left towards B, we already know that Min is going to force the final score to be -1. Not great. But if Max goes right towards C, we know Min's best move will still leave Max with a score of 2. So what's it going to be? A guaranteed -1 or a guaranteed 2? For Max, the choice is obvious. He's going for the 2.
And that's the whole magic trick right there. The best opening move is to go right toward node C. Why? Because it guarantees Max a final score of at least 2, no matter what Min does. Even with a perfect opponent, that's his floor. And there you have it. By starting at the end, the algorithm found the perfect beginning. Pretty cool, right?
So this seems amazing, right? It feels like we found the holy grail, a foolproof way to play any game perfectly. But, and this is a huge but, this perfection comes at a crazy expensive cost. Thinking about every single possible outcome has one very big problem. And that problem is called time complexity. Let's not get too bogged down in the math, but basically it comes down to this: B to the power of D, where B is how many moves you can make each turn, and D is how many turns are in the game. The key thing to understand here is that the amount of work the computer has to do doesn't just add up, it explodes. It grows exponentially, and things get out of hand fast. So, for a really simple game like tic-tac-toe, yeah, a computer can map out the entire game tree in a fraction of a second. It's totally solvable. But for something a little more complex, like chess or Go, this exponential growth isn't just a challenge, it becomes a brick wall, an impossible barrier.
And just to give you an idea of the scale we're talking about, let's just look at chess for a second. On an average turn, a player has about 35 different legal moves. That's our B. And a typical game can last around 100 moves. That's our D.
So, what's 35 to the power of 100? It's a number so mind-bogglingly huge that it has more zeros than I can count. I mean, we're talking about a number that's bigger than the estimated number of atoms in the entire observable universe. There is no computer on Earth and no computer we can even imagine building that could ever calculate that many moves. It is literally impossible.
Yeah, to put it simply, the game tree for chess is just too massive. You could never, ever explore every single branch. So using this pure, simple version of Minimax on a game like that, it's just not going to happen.
So then, how does chess computers work? How does something like Deep Blue or Stockfish do its thing? Well, they use a much smarter version of this algorithm that has a cool name, alpha-beta pruning. It's basically a way for the algorithm to be more efficient. It can look at one branch of the tree and say, you know what, this path is already worse than another one I found, so I'm not even going to waste my time exploring it any further. It intelligently chops off huge, useless sections of the game tree, which makes the problem actually solvable. Which really brings us to a fascinating final thought, doesn't it? The Minimax algorithm gives us this beautiful, perfect blueprint for how to play a game flawlessly. But its own math shows us that for complex games, true perfection is impossible to calculate. So if perfect play is off the table, how do we build an AI that's just good enough? Good enough to beat the greatest human champions in the world? Well, that is the question that drives the cutting edge of AI and game theory today.